Okay, so if we have our elliptical paraboloid that we've constructed, and we take a region of the xy plane, we can figure out a rectangular region with sides parallel to the coordinate axes. We can plug the coordinates of these points in and find out the z values, which is how high this thing would be, and there's our usual picture. We can do all the things we want to do. We can find the slope of this line, we can find the slope of this line, slope here, the slope here. We can find vectors parallel to the sides, take the cross product, and get a normal vector. And then from that we can figure out the angle that this thing makes with the region down here in the xy plane. We can do all that. For this picture, of course, the paraboloid is kind of like this, and this thing would be tilted in a direction that isn't the same as the direction of this thing, okay? But I sketch it this way because the sketch is clear. Okay, I'm not really trying to necessarily sketch this accurately, just to give you a representation of what we have and what you know you can do. And you should be sure you understand everything I just said, okay? Very simple. You've done it. Review your notes. Make sure you kind of lock it in. Well, the other part of this picture, and really kind of the final part, because we've already looked at how you would find the volume of this by integration, how you'd find the mass if you had a density function, okay? We haven't extended it to the whole surface, but we've done it for this one little region, which is really all we need. Then we just extend that to the surface in a way that you'll see later. Okay, it's fundamental to understand what happens here. Well, one thing that happens here is, let's just say this is the line x equals 2. Okay? Then and we've seen this face here is an approximation to z equals the function f of 2y. In other words, we can take the plane x equals 2, which is a vertical plane, and cut our surface with it. Okay, it won't really look like this. This is just kind of a schematic. But on this interval, water. This trapezoid approximates, or actually matches, this face of our parallelpiped, right? Our truncated rectangular parallelpiped. And the slope here is just our derivative of z with respect to y, because of course we have z going this way, y going this way, right? At whatever point, it may be some sample point within the interval. But it's the average slope. So we could say the slope is approximately equal to dz dy. Okay? Well, partial derivative of f with respect to y. It's 18y. How did I get that? Well, remember when we did an integral to find the volume and to find the mass given the density? What did we do when we integrated with respect to y? We treated x as a constant, right? Okay? Well, we do the same thing. X is a constant. Take the derivative of this thing with respect to y. That's constant. That's constant, so the derivatives are 0, so all we have is this, and the derivative is 18y, right? Also, of course, we could look at the partial of f with respect to x. And that's really easy, that's 8x. We treat y as a constant, 4 is already constant, so then we don't have this, right? Well, this is what partial derivatives tell you. They tell you the slopes of your little friend that I haven't yet gotten to you, but the truncated parallelpiped. Okay? So these partial derivatives just tell you this. And of course your picture here is you got some plane, or some plane above a line where x is constant, right? So you're cutting your surface with this plane, okay? And really what we've done here, of course, is this picture just corresponds to cutting our surface with a plane here, a plane here, a plane here, and a plane here to give us a little picture of what happens in some corresponding to some rectangular region in the XY plane. Make sense? Okay.